The numerical application we're going to be looking at is the one where we try to find the root of a function. So let's take this as an example of conducting numerical computations using Python. So here's the finding root example. What is the problem? The problem is we have a function, f of x, and this function varies continuously on the real axis. The question is, can we find the root of or a root of the function? Specifically, it will be a real number r such that f of r is equal to 0. If this is the case, we say that r is a root of f. So the question is, given a function, can we find the root or a root of this function? Now, the issue here is multiple fold. One is that even if there is a root, we may not be able to find it exactly because we're relying on numerical computations. So we may be a little bit off. So we have to accept the fact that we may actually find an approximation for the root or a root. The other question is, well, maybe there's no root to start with. Yes, well, it depends on the function. So these are the things that we have to examine. Can we guarantee that there is a root for the function that we have at hand? Two, we may get an approximation. Now, talking about the approximation, this could be done, or we get an approximation for various reasons. The most important one is that we do have some numerical computations, and numerical computations are not done with infinite precision. If you remember how we represented numbers in Python, you will see probably why this is not going to be an exact. All right, and also the numerical computation may itself be some kind of iterative procedure, and at some point we may actually have to stop. I mean, we could actually be improving our estimate as we keep going, but at some point we need to be able to do this using finite number of operations. So since it is a numerical computation-based approach, we will have to stop, and we may end up with an approximation to the root instead of finding the root exactly. We will examine three methods. The first one is called the bisection method. Second one is a method due to Newton called the Newton method, and finally the secant method. So for this example in here, we will be using a function that is nothing but x squared, and we were specifying the derivative. So this is function prime that takes x and returns 2 times x. All right. So we're using those functions as an example for what we're doing next, but we could implement any other function based on what we're going to be seeing later. Any other function that satisfies certain properties. All right, so let's talk first about the bisection method. The bisection method is rooted in the theorem, a very fundamental theorem in mathematics. So it's called the intermediate value theorem. The intermediate value theorem states the following. If we have a function that is continuous over an interval, so let's say xl for lower edge, xu for upper. So if you have a function that's continuous between xl and xu, and you pick a number that is between f of xl and f of xu, any number y that is in this range, then the theorem says, well, there is definitely an x in the interval such that f of r is y. I mean, here probably it is best seen if you, when we're saying the function is continuous, where you're drawing it, you're not allowed to lift your hand. So if from xl to xu, you draw a function without lifting your hand, then, and you're going, let's say, from f of xl, let's say this is 1, to f of xu, that is 2, and you're going from 1 to 2 without lifting your hand, then you must have passed by 1.5. And this is the idea in here. The idea is, give me any y that is in this range. Definitely, there exists an x and an r in the interval for which f of r is equal to y. So here for the bisection method, we're going to use a version of the intermediate value theorem, or an implication, and the implication is the following. If over the interval xl to xu, we start from a negative number and we end in a positive number, so f of xl and f of xu are of different signs. Vice versa, I could start positive and draw and go negative. If over the interval, I'm starting in one place and end up in another in the sense of different sign, then definitely I would cross 0. Which means there is a root, there is an r in the range xl and xu for which f of r is equal to 0, and this is the definition of a root. So the bisection method is based on this principle. Now, before we get going, we have to be careful about the fact that if we have two values that are of different signs, it doesn't mean that the root is unique. It could be that I have multiple roots, like in this diagram, right? So f of xl in here is positive, f of xu is negative. And as you can see, we're crossing 0. This is a root once, twice. So this is another root 3 times, and this is a third root. So there is no uniqueness in here. We're simply saying there is a root. So this is the first point that we have to make. 2, if we start with an f of xl and f of xu that are of the same sign, then we cannot make a conclusion. We cannot draw a conclusion. It could be that actually there are roots, like in this diagram in here. There is one root here and one root here. And it could be that there are no roots, right? So in some sense, to guarantee that the problem has a solution, we have to start from a place xl and xu, for which f of xl is of a different sign than f of xu. Otherwise, in this scenario in here, we may have a solution, we may not. But if we start with the setup that I just mentioned, we potentially have more than one solution. So our task is simply to find one root or find a root. Okay, so we're going to assume that we're starting from a good place, meaning we have x of l and x of u, and f of xl and f of xu are of a different sign. So these are inputs to the method, and the inputs in here have to be good inputs, meaning different signs. What are we going to do? We're going to do something that's very similar to binary search. We're going to aim for the middle of the interval. So let's call it xm. xm is the midpoint between xl and xu. And we're going to check the sign of f of xm. Now, depending on the sign of f of xm, we're going to be able to determine that the root or a root is present in the first interval versus the second interval. Now, how do we do that? We simply need to make sure that the interval we're choosing is going to have an f of xl, f of xm, or f of xm, f of xu that are of different signs. By the way, if at xm we hit exactly 0, then we're done. I mean, this is great. If f of xm is 0, then xm is the root, or f of xm is pretty close to 0, then actually we can stop. And kind of, this is the place where we're going to say, we did find what we're looking for up to a certain tolerance. If not, we're going to, throw away either the right interval or the left interval, and we repeat. So this is the iterative procedure. You can think about it as a recursive implementation as well, where we aim for the middle element. Depending on the sign, we either look to the left or to the right. And when do we stop? And here we're going to have multiple criteria. The first criteria will be, okay, f of xm is small enough, so this can be considered 0. So maybe I have a tolerance of, I don't know, 0.0001. I'm going to say this is really small, and this is really a value that's equal to 0, and this is the root I'm looking for. Or you get to a place where the interval is very small. So either you can get a tolerance in y, meaning the value, or a y tolerance, or a small x tolerance. This is the value of x, being there's not, a lot of work just to determine a few additional precisions. I mean, I understand that I am stopping when I get very close to x, or when I get to a place where the value is very close to 0. So these are the two stopping criteria that we have in here. Now, the great thing about this is that, if we start with 2 points that have different signs, then we're guaranteed to get to a place. We're guaranteed that this method will converge. It will stop eventually. I mean, it's not like this is a method that will oscillate or will never stop. No, it is guaranteed to converge. However, there is no guarantee of fast convergence. It could be that's guaranteeing actually rather slowly. And also, there is another issue that is related to the fact that we have to be able to start in a good place. So if you have a function that doesn't change sign, like x squared, that the one that we have before, then actually there is a root, but there is no way I can find 2 points that have different signs, right? So in some sense, we do have limitations that are related to the bisection method. The first limitation is I have to start in a place where I do have f of x, l, and f of xu of different signs. Let's talk about the implementation in here. This is the bisection method. It takes the function f. This is a parameter. It takes a and b. This is the interval over which we're working. It takes the tolerance in x and the tolerance in y. These are the two parameters according to which I will stop in case I get an x that is close to the tolerance, or the interval is small enough, the improvement is less than the tolerance, and I get a value in f of x where it is smaller than the tolerance. So here we go. We need to check over this interval a and b that we have the sign of f of a and the sign of f of b different. So we can use the sign function from numpy. So from numpy, we can import sign. Or instead of using the sign, we can simply check that the product is positive. If the product is positive, then it means that are of the same sign. So it is really, whether we want to use the sign or not, it's up to us. So if we're going to use the sign, we're going to check the sign of a number. It's either 1 or -1. 1 if it is positive, -1 if it is negative. So if we say this, the product of the sign is not -1, so it has to be -1 to enforce that they are of different signs. If not, we're going to say, well, you know what, I'm starting with a place where I have the same sign, so there's nothing to do, we're stopping, right? And this is the return 0. We're saying, okay, I'm not doing anything, I'm stopping. Otherwise, we aim for the middle value, a plus b divided by 2, and we're going to, in here, check which interval should we continue working on. So here we go. As long as I have to work, it means that b minus a, the width of the interval over which I'm working, is actually bigger than twice the tolerance, because this is going to guarantee that the middle point, the midpoint that I'm choosing as an estimate, is bigger than x tolerance, all right? And then I'm computing f of c, right? We're denoting this in here, f of z, and then we're going to check, is f of c small, very small? If it is very small, I'm stopping and I'm saying, okay, c is the root. If not, I have to check the sign. If the sign of c is the same as that of b, I should work on the interval ac. Okay, so in here, we are changing the value of b to c. So the interval for which I'm working, a to b, becomes a to c. Now, if the sign of b is not the sign of c, then I should be working on cb, which means repeat everything while a becomes equal to c. So this in here, this is the repetition structure. We'll have to keep working in here as long as the interval is big, bigger than twice the tolerance in x, and in here, so this is the return statement, and the value of f of c is bigger than y tolerance, all right? So this is how we go about computing this. So this is the implementation of the bisection method. Now, you can run it on, and here we're not going to be able to do it because the function we're looking at is x squared. So we're giving the value -0.2 and 9, and here we're saying, okay, oh, wait a second, the same sign of the initial value, so we're stopping. So let's go back and change the function and choose a function for which we have a root, and the root is a place where we're changing sign. So instead of x squared, we're going to go for x cubed, and the derivative would be 2x squared. So in here, we didn't use, sorry, 3x squared. Here, we didn't use the derivative, but in the other methods we will discuss later, Newton methods, we will be actually using f of x function prime. Okay, so for the moment, let's take x cubed, and we're going to run the bisection method on x cubed. So here, bisection, we're starting from -0.2 and 9. So let's say if we give it 0.2 and 9, the same issue, because x cubed at 0.2 and x cubed at 9, both of them are positive. So if I start from minus, let's do 2 in here, to 9. Okay, so what did we do? We started with a place that is negative. -2 cubed is -8. 9 cubed becomes something that's large. And then we're going to iterate in here until we get within the tolerance. The tolerance in here, we're taking 10 to the -5 in x and 10 to the -4 in y, and it keeps iterating, and we're saying, okay, you know what? I got an estimate of a root, actually a root for x cubed in here in this interval is 0, and this is what it is. Now, if we wanted to stop a little bit earlier, and you can see that, you know, the estimate is 0.06, and let's say the tolerance is 10 to the -2 in both, and this is it. If you want something that's seriously smaller, so let's add a few zeros, and you can see that we're approaching the root. And here we're stopping because the value at which the value we're computing at the middle point is either too small, or the window over which we're working became too small. All right, so this is the numerical method that is based on the bisection method. And as we said, it is guaranteed to converge. Its inconvenience is that we need an initial guess that is good. Yani f of xl and f of xq are of a different sign. It will not work on functions that do not change sign, because, you know, the way we are implementing it, it's not going to work. And 3, it is rather slow. The convergence is not as fast as other methods. So in the next video, we'll look at the Newton method.